Hello everyone, Mr. Fawcett here, and today we're going to look at some geometric proofs. So last couple videos we talked about algebraic proofs, which are a good place to start because we use a lot of those same properties in our geometric proofs. Then we just expound and have to use some geometry reasons, theorems, and definitions in addition to the algebraic properties we're using. So before we get into some more proofs, let's first do a quick little warm up to get us thinking. You got 4 problems to do. One of them is just a joke, so really just 3 problems to do and 1 to read for fun. Pause the video when you're done and you can check your work. Okay, so the first one says if 2 angles are congruent, then they are So if 2 angles are complementary, then they are not congruent. So we need to determine whether the statement is true or false. If it's false, we need to provide a counterexample. So if 2 angles are complementary, then they are not congruent. Well, is it possible for 2 angles to be complementary and also congruent? Well, complementary just means they need to add to 90 degrees. And what if I just have 2 45-degree angles? Right? Those would be congruent, and they would be complementary. So here's our counterexample, which means this statement is false. It is possible for angles to be complementary and congruent. Number 2 says if 2 angles are congruent to the same angle, then they are congruent to each other. This is an example of the transitive property. So I'm going to write this out algebraically, actually. If I have angle 1 congruent to angle 2, should have my angle symbol there, and I know that angle 2 is congruent to angle 3, well, this would imply that angle 1 is also congruent to angle 3, right? If angle 1 and angle 3 are congruent to the same angle, angle 2, then they have to be congruent to each other. This statement is true. There is no counterexample. Number 3, supplementary angles are congruent. So supplementary means they need to add to 180. However, they don't have to be congruent, right? We could come up with 2 angles. Let's do 50 degrees, and we'll do 130 degrees. Those are supplementary, but they are certainly not congruent. So this statement is false. The 2 angles could be congruent if they were both 90 degrees. They just don't have to be. And then hopefully you enjoyed the joke about this kid asking for a raise of an allowance, and the dad, after having taken a management class, decides that that is not in his best interest. All right, let's get into some proofs. Before we start actually doing some proofs, though, I said, let's get into some proofs, and then I said, hold up a second. So we do have actually 2 things to do first. This first one is just asking you to think about why it's important to be able to prove something. And how does this make math different from some of our other disciplines that you may be involved with, like history, English, music, etc. So take some time, answer this question, write down an answer, and then you can see if yours matches with what I'm thinking. Okay, so I'm not going to write down everything. We'll just have a short discussion. One of the reasons proofs are so critical to mathematics is that if no one was able to prove what we were doing, how would we know that it was correct? Right? When new math is discovered, people can't just say this is how it works and go implement this, right? When new math is discovered, people write a paper on the proof on why it works, right? They have to defend what they're thinking, what they're saying. If someone comes up with a new equation for something, whether it's in physics or biology or economics, they have to prove why that equation works. They can't just come up with it and say this is true, right? And then teach it to a bunch of people. People aren't going to listen to them until they know for sure that that equation is true, right? There has to be some logic behind it. So, and you guys should think the same of what I'm teaching you, right? If I teach you something, I want you to ask why. I don't want you to just take it and think, oh, it must be right because Mr. Falsett's my teacher and he said so. I want you to challenge me on it. I want you to say, well, why does this work? Why is this true? Why, just asking the question why. Those are never bad questions. Those are questions that help you get to the core of whatever you're studying. And you want to be able to know the why, right? Because if you leave class and you're able to do the technical work, the work of solving equations and kind of just understanding what to do for different problems based on, what you've seen before, that may help you score well in a test. It may even help you get a job and be successful at certain jobs. But you're not going to have a complete understanding. You're not going to, if you don't understand why you're doing something, there's a whole part of your learning, there's a whole part of your knowledge that's just completely left out. One of the problems with not knowing the why or being able to explain what you're doing is that you could never teach somebody else what you're doing. So, let's say you get a job, let's say you get a job as a carpenter, right? It's one of the jobs I worked for a couple of summers, so I have a little bit of knowledge. But when I was on the job, a lot of times they would just tell me, here, you need to do this. But they'd also want to tell me why I was doing that, right? So that when we got to a new house or a new job site, I'd have a little bit more knowledge and I'd be able to do some problem solving on my own, right? If you're just telling someone what to do, right, but you're never explaining why they're doing that or how that factors into the overall picture, they're not going to be as good of a worker, right? They're not going to understand it as well as they need to. So as a teacher, it's a question that I like to ask quite a bit, is the why. And as a student, I want you to also ask me why. I want you to ask me why so that you're then able to explain the work better on your paper and to the other people that you're talking to about whatever subject it is. Okay, we could go off on hour or more tangent on this topic, but we do need to get to the actual math for what you need to know for this unit. So if we look at the structure of these proofs real quick, just to reiterate, we're doing 2-column proofs, right? So we have a column with our statements and we have a column with our reasons. The first line of your proof is usually going to be some given information. It doesn't always have to be, but generally it's going to be. And that's because that's the information that you're going to work with the rest of the proof. Everything in your proof has to come from somewhere. And the given information is the only information that you don't have to think about, oh, where did that come from, right? You can just write down that it was given. The last line of your proof should be what you're trying to prove. And the in-between steps are the logical steps that you can justify with definitions, properties, postulates, and theorems. And again, remember, we're not trying to leave any steps out. Even if you think it's a step that whoever's reading your proof is going to understand, you can't leave it out, right? You want to assume that I think we talked about this in a previous video, but you want to assume that you're writing these proofs for someone who doesn't know virtually anything about the topic, right? So you're basically, you could think of, teaching an elementary schooler. You need to write your proof so that someone with very little knowledge would have a chance at understanding what's going on. And if you're leaving out steps, that's going to be a lot less likely to happen. It's not going to be a complete proof. Before we start getting into these geometric proofs, we are going to look at these definitions, theorems, postulates, and properties at the back of your packet. So these are just the new properties that we're going to be using in our reasons column, right? We did a bunch of these for our algebraic proofs, like the addition property of equality, the subtraction property of equality, the symmetric property of equality, the substitution property. So there's a lot of these, right? And it may seem like, how am I ever going to remember all these? You're not today. Okay, you're going to reference this sheet a lot when you're working through these problems. But gradually, as you complete more and more proofs, these are just going to be like vocab words, right, from English. When you first learn vocab words, you may have to keep looking up the definition. But the more you use them in your writing, the more you read them in books, you don't have to keep looking them up anymore, right? They just become second nature to you. So eventually, that's the point I hope to get you to. But for now, I understand that you're going to be referencing this sheet a lot. So I'm going to do one at a time. We'll write it out. We'll discuss it. And we'll see if we can get through one proof afterwards, but we may have to save the proofs for part 2. All right, so first we have the definition of complementary angles. These are pairs of angles whose measurements sum to 90 degrees. So I have 2 examples for you. I have 2 angles in pink, 30 plus 60 equals 90. So these angles would be complementary. I also have another example in red. Now I don't have any measurements here, but these 2 angles, there is another way we know that they should be able to sum to 90, right? And that's strictly through this little box right here, right? The box says at the end, the big angle, the red angle, is 90 degrees. And if I've split that into 2 angles, it doesn't matter what their measurements are, the sum is going to be 90. Next, we have our definition of supplementary angles. These are pairs of angles whose measurements sum to 180 degrees. First example is in brown, when the angles are not adjacent. 110 plus 70 gives us 180. And then I have a linear pair here. I have a red and a green angle. We don't know their measurements, but we know that whatever the measurements are, they would be equal to 180 because they both form a line. So they're a linear pair. We next have a theorem, the vertical angle theorem, and this theorem says that vertical angles are congruent. So if we see 2 vertical angles in a diagram, we can say that they're congruent. I have 2 examples. Remember, vertical angles are angles that are across from one another when 2 lines intersect. And we're basically looking for x's on our diagram. Now, the vertical angles can be on the top and bottom of the x, or they can be on the left and right-hand sides of the x. All right, so we then have the angle addition postulate. Quick side note, theorem is something that can be proved, whereas a postulate is just something we take for granted. Same with definitions. So definitions and postulates, we don't prove those. We just take them for granted. Theorems are something that can be proved. So the angle addition postulate says the measurement of 2 adjacent angles will equal the measurement of the larger angle that they form. So if we come over to the diagram, the larger angle is angle ABC. So the measurement of that angle is going to be equal to the measurement of the 2 smaller ones, ABD and DBC. All right, let's scroll on down, see which property is next, or in this case, a theorem. All right, so we have the linear pair theorem. This states that linear pairs have measurements that sum to 180 degrees. So remember, linear pairs are adjacent angles that form a line. So in our diagram, angles 1 and angles 2 form a line. That means that the measurement of angle 1 plus the measurement of angle 2 is equal to 180 degrees every single time. So I did the next 2 together just because they're 2 simple definitions for right angles and straight angles. Right angles have a measurement of 90 degrees. So if we have a right angle ABC, that measurement is going to be equal to 90. And straight angles have a measurement of 180 degrees. So measurement of angle ABC in green is going to be equal to 180 as long as A, B, and C are collinear. All right, the definition of congruent angles. This has 2 parts, and you can go either way. Congruent angles have the same measurement, and angles that have the same measurement are congruent. So in purple, if we know that angle 1 is congruent to angle 2, then we know the measurement of angle 1 is equal to the measurement of angle 2, and vice versa. So in maroon, if the measurement of angle 1 equals the measurement of angle 2, then angle 1 is also congruent to angle 2. So this is a property you'll use a lot, and you just want to be aware that you can use it going either way, either from congruent angles to angles that have the same measurement, or from angles that have the same measurement two congruent angles. All right, onward we go. We're getting close to the end. Have three more. All right, so the definition of angle bisector. An angle bisector splits the angle into two smaller angles that are congruent, or that have the same measurement. So over here in maroon, if ray BD bisects angle ABC, so our angle bisector is this ray right here, then two things are true. We can say that the angles are congruent, the smaller angles, ABD and DBC, and we can say that they have the same measurement. The same thing is going to be true with the definition of segment bisector. So the definition of segment bisector, a segment bisector splits the segment into two smaller segments that are congruent, which also means they have the same length. So in our diagram, AB is our segment bisector for segment CD. So if the blue segment bisects the red one, then we know that the pieces of the red one, so CE, E is that point also on CD. So CE is congruent to ED. Those two segments are congruent. And we can also say the lengths of those segments are equal. So coming down here, remember, if I leave the bar off of these letters, that means I'm talking specifically about the length. So the length of CE is equal to the length of ED, whereas up here, I'm saying that segment is congruent to the other segment. Saying something's congruent and that something have the same length are very, very similar, especially when we're talking about segments. One is just talking about the entire figure. So they're saying segment CE is the exact same segment as ED. When we get into our definition of congruence, you'll have a better idea of what that means. Whereas the other one is strictly just talking about the lengths of the segments. Okay, actually lied, I guess, back before. We do have one more after the definition of midpoint. I've got to add it in here. I just remembered. So two more. All right, so the definition of midpoint. A midpoint splits a segment into two smaller segments of equal length. So if A is the midpoint of segment BC, then the length of BA is going to be equal to the length of CA. So we're just talking about the lengths for the definition of midpoint. Okay, so I do have one more for you. This is going to be the definition of congruent segments, which is essentially the same as the definition of congruent angles as we saw up above. So it says congruent segments are equal in length, and segments that are equal in length are congruent. So for the brown over here, if segment AB is congruent to segment CD, then the length of AB is equal to the length of CD, and vice versa. If the length of AB is equal to the length of CD, then segment AB is congruent to segment CD. So I know that was a lot, but we had to go through these properties if we're going to be able to do our proofs correctly. So the boring part's over. Now we get to apply. I look forward to seeing you back for part 2, where we get to put these different properties, theorems, and postulates and definitions to some use. So as always, enjoy the rest of your day.